Okay, so at first glance you think, hey, finding the area of the circle, piece of cake. I know it's going to be pi r squared. Well, that's because in geometry someone told you that's how to do it. But how do we know for certain that's really how it gets done? So we're going to use calculus. We're going to find the area of a circle using calculus. So of course, there's our calculus cal. Go away, calculus cal. Thank you. All right, so we want to find the area of a circle, but we'll be using calculus to do this. And yes, we will be revisited by that cornerstone, that building block of foundation of trigonometry in just a little bit here. Okay. Now, hopefully you remember the equation of a circle when it's centered at the origin. It's just x squared plus y squared equals radius squared. And then, of course, sometimes it's not centered at the origin. And so if the center is at some other location, such as h comma k, that's what the equation looks like. Right? You know it's not a parabola because both the x and the y are squared, right? If only one of the variables is squared, then you know that it's a parabola. If they're both squared and both positive but different coefficients, then it's an ellipse. If they're both squared but one's positive, one's negative, then you know it's a hyperbola. But in this situation, both variables, x and y, are squared. They're both positive and they have the same coefficient, so it is a circle. So today we are going to work on finding the area of a circle represented by the equation x squared plus y squared equals 100. And of course, if it's equal to 100, well, the radius must be 10, right? Because 10 squared makes 100. So this circle is centered at the origin. It has a radius of 10. Right, so let's take a look at a circle of radius 10 centered at the origin. No, Bob Ross, that's not really what I needed. I needed a circle with a radius 10. Okay, so there is a circle with a radius 10 centered at the origin. Notice from left to right on the x-axis, it'll go between negative 10 and positive 10. Notice up and down on the y-axis, it also goes between negative 10 and positive 10, right? Because the radius is 10. Okay, now remember, when we are finding area, we're cutting the region up into a bunch of rectangles. And of course, the rectangles don't fit in there perfectly, but the skinnier and skinnier we make those rectangles, the better and better they fit. And so if we cut it up into n rectangles as n approaches infinity, it's like, hey, the thickness is always dx, but what is the height of that rectangle? Well, it's the upper curve subtract the lower curve. So it's like, well, if I want to know the value of y, I better start by subtracting x squared. Undo the squared by taking the square root. And you're like, oh, well, when it's a positive square root, that forms the top half of that circle. That's our upper limit. They're our boundary. When we have the negative in front of the square root, you're like, oh, that's the bottom half of the circle, the lower boundary. And so to set up our integral, well, for the area, we're going to integrate from negative 10 to positive 10, because that's the direction we need to go on the x-axis. And then we've got the upper boundary, subtract the lower boundary. Hey, subtract a negative. Look what's in the middle there. Subtract a negative. We just have addition. And those are identical, so we just have two of those square roots, right? We have two of the square roots of 10 squared minus x squared. Uh-oh. I don't think this is something we can integrate. So now we need the triangle, but I'm going to skip Bob Ross. All right, we've had enough of these Bob Ross jokes here, so we're going to go straight to the triangle. Of course, it's going to be a right triangle, so I need that 90-degree corner. And then I have to put theta in one of the acute angles. It does not matter which angle I put it in. But once I decide on which angle will be theta, I now know which side is opposite and which side is adjacent. And of course, in a right triangle, we know a squared plus b squared equals c squared, where c is the hypotenuse, a and b are legs. And so if I want to know like leg A, it'd be like, oh, well, leg A is easy. You take c squared, you subtract b squared, and then you take the square root. And of course, if I look at the integral, I'm like, hey, that's what I've got in the integral, right? I've got 10 squared minus x squared. So x is one of the legs, right? X is one of the legs. And of course, 10 has to be C, right? 10 is the hypotenuse. And of course, then the other crazy leg, well, that's going to be the square root of 10 squared minus x squared, right? And that's the side we want to avoid using because that's really messy. So for our substitution, we're going to have to use the sine function because x is opposite theta and 10 is the hypotenuse. Sine is opposite over hypotenuse. So sine of theta will be x over 10. Right? Because I'm trying to substitute something for x. So let's multiply both sides by 10. And x is equal to 10 times the sine of theta. So I can substitute that in to the integral, but oops, the integral is going to dx on it. So let's take the derivative of x with respect to theta. Of course, the 10 will sit there because it's a coefficient. The derivative of sine of theta will be cosine of theta. Multiply both sides by d theta. And now that I know dx is just 10 cosine theta d theta. So I can substitute just about everything. Oops. The limits of integration. Those are written for x. We're trying to change to theta. Like, well, if sine of theta equals x over 10, let's plug in, well, let's solve first, my bad. Let's solve for theta. You say, hey, theta is going to be the arc sine of x over 10. Now we can plug in that negative 10. So I need the arc sine of negative 1. Now here's where it gets a little bit tricky, right? If you're looking at your unit circle and you're trying to figure out when does sine have a value of negative 1, you're like, whoa, what is this answer? Negative pi over 2? What just happened? That's not what I expected. So we have to talk a little bit about the arc sine function and how it's different than just solving an equation. Right? If I just wanted to solve an equation, let's pretend I said, hey, sine of theta equals negative 1. You're like, well, gee, that happens at 3 pi over 2. Theta must be 3 pi over 2. Because when we're solving that type of equation, we assume theta is somewhere between 0 and 2 pi. The issue is the arc sine function has a domain of negative pi over 2 to pi over 2. So that's why we're coming up with a negative pi over 2 instead of a 3 pi over 2. It's the same location, but because of the way the arc sine function is defined, we have to use the negative pi over 2 instead. Okay, so that's why we've got a negative pi over 2. Now, of course, x also could have been positive 10. So instead of just doing negative 10 over 10, I have to do positive 10 over 10, which reduces to 1. And then, of course, arcsine of 1 is pi over 2. So now I can rewrite my integral. All right? Now, I still have my integral symbol. I still have that 2. I still have the square root symbol. I still have 10 squared. I still have subtraction. And then whatever is going to replace x is still getting squared. But instead of going from negative 10 to positive 10, we're now going to go from negative pi over 2 to pi over 2, because those are the values we got when we switched from x to theta. Of course, instead of x squared, we're like, hey, we know what x is. X is going to be 10 times the sine of theta. So I'm going to have 10 times the sine of theta squared. And then, of course, instead of dx, we're going to use 10 times cosine theta d theta. Whew, boy, that's a mouthful. And I'm thinking, wow, this is look even worse than what we had before. Well, what can we do? Well, if I'm looking inside that square root symbol, I'm thinking, well, you know, 10 squared is 100, right? 10 times 10 is 100. And then 10 sine of theta multiplied by 10 sine of theta. Well, 10 times 10 gets me the 100. Sine of theta times sine of theta gives me sine squared of theta. Hey, inside that square root symbol, I see a common factor. I see a common factor of 100. So I can factor out that 100. Leaves me with 1 minus sine squared theta. And of course, we can go to our cornerstone, our capstone, our foundation, and say, hey, just about everything that we use in trigonometry, we can derive from sine squared theta plus cosine squared theta equals 1. So if we replace the number 1 with that, we'll notice that we can get sine squared theta to cancel sine squared theta, leaving us with cosine squared theta. And that's something we can take the square root of. Square root of 100 is just 10. Square root of cosine squared theta is just cosine of theta. And then if we simplify that, 2 times 10 will get us a 200. Cosine theta times cosine theta gives us cosine squared theta. Whew. Oh, we still cannot integrate that. But we got a real nifty trig substitution that'll save the day for us here. I know that cosine of 2 theta equals 2 times cosine squared theta minus 1, right? That's one of our double angle identities. And so if I've got cosine squared of theta, I'll say, well, I can add 1 each side, and then I can divide. Oops, I don't want to divide by 2, right? If I just want cosine squared theta, I could divide by 2, but I'm like, hey, if I look inside the integral, there's a 200 on that cosine squared theta, right? Not a 2, but a 200. So that's why I multiplied everything by 100. It's like, okay, so I can replace 200 cosine squared theta with 100 plus 100 cosine 2 theta. And now we have something we can integrate. Right? When I integrate, it becomes 100 theta plus 50 sine of 2 theta. And we got to evaluate that at pi over 2 and negative pi over 2. Now, if you're wondering, where did all those pieces come from? Well, if you just think about integrating the number 100, you're like, oh, well, let me see. It must have been 100 theta then, right? Because of y equals 100 theta, if I take the derivative, I get plain old 100. So that's why we have that 100 theta. Now, if you're wondering, where does that 50 sine of 2 theta come from? Well, if I want to integrate 100 cosine 2 theta, handy u substitution, right? And when I do that u substitution, notice I get a 1/2 du. And that's why that 100 became a 50, right? 100 times a half is 50. And of course, if I integrate cosine, I get sine. And now if I do my back substitution, u becomes 2 theta. So that's how that integration happened. So we are done integrating. Now we just have to plug and chug. Let's plug in the values, come up with an answer. So every place I see theta, I have to replace it with pi over 2, get that answer figured out. And then I got to do it again by replacing every single theta with a negative pi over 2, figure that out. And I take the first answer, subtract the second answer. Now, first things first, I can do some basic fraction work and say, hey, 100 times pi over 2, that'll be 50 pi, right? Half of 100 is 50. 2 times pi over 2, well, that's just going to be pi, right? So there are a lot of fractions I was able to simplify there. Hey, sine of pi is 0. Sine of negative pi is 0. Right? If I look at my unit circle, and if I go to pi radians, the value for sine is 0. Or if I go backward around that unit circle, right? Start at 0 and go backwards pi, you're like, hey, look where I am, right? Value of sine is going to be 0. So 50 times 0, of course, is 0. And so all we really have is 50 pi subtract a negative 50 pi, also known as 50 pi plus 50 pi. And so the area of that circle with radius 10 is 100 pi. And of course, because it's area, it is square units. Now, if you want to see what we did step by step the whole way through, here it is, right? Step by step, the entire way through the process, including an inset with the triangle to show where that substitution came from, and the inset showing how we converted from the x coordinates to the theta coordinates. And so there is all the work in one screen. Now the worksheet has just one question for obvious reasons, right? That one question might take up, oh, I don't know, 30 minutes worth of time. It's going to be a lengthy one. I'm going to have you try find the area of a circle with a radius of 3. And of course, because it's the area of a circle, you probably know the answer before you start. You're like, oh, come on. I know the answer is supposed to be pi r squared. So before you even start, you know what the answer should be, but I want you to go through with the calculus and see if you can get the area using calculus.